In the last video, we brought our sensor objects to life. Our sensors boot up, they remembered who they were and the job they did, and when the mission was over, they shut themselves down like real autonomous modules. Each one had a name, a job, and its own memory. We even built two separate sensors. We had the temperature sensor and the gyroscope sensor, and each acting independently. But I want you to look closer, and you'll see something strange. They all share the same behavior, the same startup, and if we add here calibration and display logic, they would share a similar feature. Imagine if this machine keeps growing and we had like 5 sensors or 10 sensors, 10 modules, a fleet of hardware all running the same patterns. Do we just copy the same class over and over? No, that's like a trap. Because real systems don't grow by duplication, they grow by evolution. This is the turning point, the moment where modular design becomes machine evolution. And the key to that evolution is inheritance. And that's the core of this video. One of the core principles of intelligent system design, and that's inheritance. It's the same thinking that runs satellites, surgical robots, real-time aerospace systems, and much more than that. Imagine you design a perfect sensor. It reads a value, calibrates itself, and prints to the screen. Now you want it to make another sensor, like a temperature sensor and a gyroscope sensor, but they both need the same features. Do you copy and paste the same code again? No, that's like asking for bugs. Instead, you say, I already built this logic once, can I reuse it? But give it a new name and maybe a twist, and that's inheritance. In real life, you inherit traits from your parents, like eye color, height, maybe even your sense of humor. In C++, classes can inherit traits from other classes. One base class holds all the shared logic, and the other classes, or let's call them the child classes, they say, okay, I want to start with that and maybe add more. Okay, so now let's build the shared brain, one big class, our base class, something that all our future sensors can inherit from line by line, and then we'll see how that goes. I think when I start with the building the code, you will have a better understanding about inheritance. All right, so let's start fresh, okay? First, before we get started, let's include the IO stream and using name space st. Okay, so first we're going to start writing class, and then we are going to call it sensor. This is the blueprint. Every sensor we're going to build now, whether a temperature sensor, gyro sensor, or light, will follow this design. Think of it as the parent that gives structure to all the other classes, okay? And inside the class, the sensor class, we're going to add protected and public, okay? So notice here, I said protected and I didn't say private, okay? And this is where things get interesting. Here, I'm just saying basically the details under here, under the protected section, are not visible to the outside world, but they're still available for anything built from this blueprint. It's a way of saying keep the internal safe, but make sure future sensors can still use them. That's how we design for reuse without exposing everything. Because if we put this as a private, we won't have this feature. Okay, and inside the protected, we're going to add 2 variables, string sensor ID and float value. Okay, so the sensor ID, this gives each sensor its own name, and it'll assign a name for it. So if we create a temperature sensor, its ID might be like temperature sensor. If we create a gyroscope sensor, its ID is gyro sensor. The second one, float value, it's basically this holds the actual measurement. It could be like a temperature in Fahrenheit, and then or a rotation. speed, or any real world number that you can think of. So next, we're going to move to the public section. In the public section, everything here is what the rest of the program can see and use. Think of it as the official controls, the switches and the buttons, and these are available for the outside world to interact with this particular class sensor. Okay, so in the public section, first we're going to start with our constructor, and then since we are building a constructor, we're giving the same name as the class, and then we're assigning string ID. Okay, and then we are assigning sensor ID to ID, and then setting the value to 0.0. Okay, so here we pass in a name and it sets the value to 0. Okay, it's just basically like plugging in a brand new sensor and watching it reset to default settings before it starts working. So right now we're going to build a simple calibration function by starting with void calibrate and bracket, and then inside we're just gonna subtract 0.5. Okay, so very simple calibration function, subtracts 0.5. That's just a little stand-in for real calibration, what real calibration does, correcting a drift, noise, or offsets that every sensor eventually builds up. In real world, calibration is what keeps your sensors trustworthy. Okay, for the sake of this example, we made it simple, just subtract 0.5 from the value. Then we're going to jump to the display function. So we're going to build the display function starting with void display, and we're going to just call cout the sensor ID and just add a gap here and the value as well, and we end the line. Okay, one thing I want to add here is the word virtual. So first, this is a display function. It prints out the sensor's ID and its current value. Okay, but notice the keyword virtual. That's a signal to C++. It means basically this function exists now, but we are leaving the door open for change later. Because one sensor might show, let's say the temperature sensor, it comes with different units. So it might show like in Fahrenheit or a different unit. Another could send its data wirelessly. So by making this function virtual, we are building flexibility into the design. The system can adapt, evolve, and behave like the real hardware it represents. So here's what we just built so far. Internal data that defines identity and state, and constructor that powers the sensor on, a calibration step that keeps it accurate, and a display function to show its current reading. Okay, and that's already a full working module. But here's the real power. Any other sensor we design, like temperature, gyroscope, light, pressure sensor, we can use this exact same structure. They would automatically get all this behavior without us rewriting a single line. All right, so now let's create a new class, and we call it the temperature sensor class. Okay, before we do that, let's just not forget this. Okay. All right, so we're going to start by saying class, and then we call temperature sensor. And then notice what I'm going to do here. I'm calling public and calling this sensor. Okay, so here I'm creating a new class called temperature sensor. The part public sensor here means temperature sensor is built on top of the main sensor class. Basically, what's going to happen is it automatically uses everything we already wrote in the sensor class, the ID, the value, the calibrate function, and even the display function. So instead of starting from scratch, this new sensor already knows how to behave, okay? And by the way, that includes the sensor ID, value, calibrate, like even the protected variables, because that's one of the reasons we changed from private to protected variables. Because if we did that as private, we won't be able to pull these variables. All right, so now I'll add the public section. So the public section, okay. So here, as we talked about this before, the public section will define the functions and controls that the rest of the program is allowed to use for temperature sensor. Then inside the public section, I will add the constructor, basically a constructor that takes an ID. So it'll be temperature sensor, and then takes an ID and will assign. So it'll take an ID and then passes that ID directly into the sensor, the big sensor, the main sensor class constructor, using sensor ID. Okay. So this line is very important because it tells the base class, you handle the setup, I'll just reuse it. We don't need to rewrite the power on logic or reset the value to 0. It's already done for us. Okay. And that's it. We'll just add this. So temperature sensor is defined. It didn't need much code because it inherited all the heavy lifting from the big main sensor class. Okay. And I think now we can create something wrong with this one. Yes. So here, we'll just do this and we're all set. Okay. Add the brackets. Okay, so now let's create another class, and then let's create the gyroscope sensor or GyroSensor. Same idea. It's built on sensor based on the main sensor, so it inherits all the same behaviors. So we'll say class, and then we're going to call gyro sensor. Okay, and then we'll call the main sensor class, then open brackets, and then inside we'll add public, and we'll call GyroSensor, or yeah, GyroSensor, and then assign string ID, and then we'll call the sensor ID constructor. All right, and we're all set. So let's just see what we did here. Okay, we create another GyroSensor, same idea. We inherited all the stuff from the class sensor, but now different name, same foundation. Okay, under the hood, it still calibrates, displays, and stores values, because both of them, temperature sensor and GyroSensor, shares the same blueprint. And as you can see, I'm not doing much. I'm just calling, creating the class, and then using everything that we just built in the main class sensor. Okay, so we've now got two real machine models. They act independently, but they were built from the same DNA. And that is inheritance. And in embedded systems, robotic, aerospace, for example, this is how you scale behavior, or at least in C++. You write logic once and build a system full of components that all know how to use it. But here's something powerful that you should know about. Just because two modules inherit the same logic doesn't mean they have to behave the same. Sometimes you want a sensor to display differently, or calibrate in its own way, or send its data in a unique format. Inheritance gives us a tool that is so cool, and it's called overriding. So let's say that this gyrosensor wants to display things a little bit different from the temperature sensor, which is now both of them are using, or they have access to the display function, this one, which they can use. But since I want to make things a little bit different for the gyrosensor, what I can do is I can create a function, a display function, that is specific to the gyrosensor. And that's where override comes in, the term override. So here I'm going to say void display And then I will add override, open a bracket. And now what I want to call here is different from the original display function in the main class. It'll be like gyro. So this is like a custom behavior specific to the gyrosensor. And then I will say angular velocity, and then add the value, and I'll just give it like radius per second, and then I will end the line. And here we have it. Something wrong here, which is basically I forgot to mention the cout. Okay, and here we have it. Now this is a custom behavior. Instead of the generic output that we have, the gyrosensor now prints the gyro angular velocity and shows the value in radius per second. And I want to get back to the override. What does it mean? It tells C++, yes, I know the base sensor class already has a display function, but this one is specific. This one that we just built is specific to the gyrosensor. So I want you to replace it with this function, and I want you to use this one for the gyrosensor. Okay. This makes the module speak in its own language, while still keeping everything else, calibration, storage, setup, exactly the same. So the gyrosensor has everything, access to the calibration, storage, the protected variables, but also has its own display function. Okay, and that's it. We've just given this sensor its own voice. Now look at the full class. We didn't change much. Just this small override, which it's a tiny change, but transform behavior. Okay, so now let's test it and see how that goes. So we'll start with integer main, open a bracket. First, I'll create a temperature sensor called TMP, basically. I'll be like temperature sensor and just call it like this. And then inside, I'll just basically add temperature. So okay, and then for the gyro sensor, I'll just call an object gyro, and then I will give it a name as gyro. Okay, and we'll create the calibration, or we'll call the calibration basically. So it'll be temp calibrate. You can see it right here, and then I'll ask basically to display the data. So it'll be temp, and then it'll be display. All right, and then we can do the same thing for the gyrosensor. So we'll just call the object, and then we'll basically calibrate, and then gyro dot display. Okay, same steps for the gyro, but remember now display is what for the gyrosensor is overridden. So we did a completely different or a little bit different display function than the temperature sensor. So when we call the display function here, it should for the gyrosensor, it should not give us this one. It should give us that one. Okay, and then lastly, we're going to just return to 0 to complete the program or to finish the program. So now let's run the compiler and see. So we're going to run it, and here we go. So we have the temperature minus 0.5, and then look at the display of the gyrosensor. Angular velocity is minus 0.5 radius per second. We can just clean it up here just to kind of add this, and then all right, let's see that again. Okay, so here, notice that both of them are minus 0.5 and then minus 0.5 radius per second. So the display function is different from the display function in the temperature, okay? And we can add other functions. For example, we can add the read function and basically add a value, and that value will be subtracted from the 0.5, and then it can give us a result. We can also add from the past video where we did the power on and power off, the constructor and destructor functions, where basically we can add just like a real modular system where like first it powers on the system, and then it basically read and then calibrate and then display the function and then shut down after that. And I think that would be a great complete project. And remember, all these functions that we can add here, you can find the common functions in the class where you can basically use inheritance to take advantage of it. So if the power on, power off, and basically powering it on and shutting down the sensor, you can use that for both sensors. So that would be in the inheritance. And then if you want to use the override term to add specific functions for certain sensors, you can do that as well. The read function as well. We can add the read function in this main class where it gets used here and there. And I can do that in the next video for sure. So let's take a step back, okay? What we just built here is we created a base sensor class. Then we made specialized versions, temperature sensor and gyrosensor. They inherited behavior, reused logic, and even customized part of it using the override basically. Without inheritance, every time we want a new sensor type, we copy and paste the same logic. That means tons of duplications, fixing bugs in five different places, and a messy structure that is really hard to manage. And that's what happens in real projects. Systems grow very fast, and suddenly your code turns into a maintenance nightmare. With inheritance, the picture is completely different. We write the logic once in the sensor class, and every other sensor automatically will reuse whatever functions and variables in that main sensor. If we fix a bug or improve calibration, that improvement applies to everywhere instantly. And when we need a unique behavior like the gyrosensor, what we did for the display function, we just use the override on that particular function. No mess, no duplication, just clean modular design, okay? So the takeaway, this is why inheritance matter. Reuse, maintainability, flexibility, and structure. You have the reuse, which is one base class, many specialized modules. Maintainability, fix once, improve everywhere. And flexibility, override only what needs to change. And then lastly, structure, a clear hierarchy instead of a scattered code. Think about real drone. It might have GPS sensor, IMU, barometer, thermal camera, you have LED sensors. Each one is a sensor, but each one displays differently, calibrates differently, and maybe even updates on a different schedule. You can't just build that by copy and paste logic into hundreds of files. You need structure, and inheritance give you that. By designing smart class hierarchies, you create systems that grow without becoming chaotic. That's why aerospace, medical, robotics, automotive, all of them rely on this type of thinking. Real machines have families of components, and inheritance is the language of those families. So far, we've created a clean structure for our modules. We inherited shared logic, customized behavior, and simulated real-world thinking. But there's one part we haven't touched yet, and that's startup logic. How does each module begin? How do you give a sensor its ID? How do you set its safe range or calibration values at the moment it powers on? That's where constructors comes in. And in inheritance, constructors behave in a very specific way. In the next episode, we will explore exactly how to build smarter modules, and we'll pass data from the child to the parent, basically. I'm talking about child classes to the parent classes, extend constructor logic, and model how real sensors boot up. And that's what we're going to do next. See you guys.